All right. So today we're going to be talking about global symmetries, representations, and Lie algebra. Might not get to Lie algebras quite in this lecture, but I'll set the stage at least. So a summary of what we discussed in the previous lecture. Let's start there. We said that there are differential symmetries of the local action that we were using to describe our dynamical system, our physics, our physical model. And we discussed Noether's first theorem that says every time you have differentiable symmetries of your local action, you obtain conserved local currents, right? So how did we do that? We took the space-time manifold, right? We took a finite region of space-time, we called it B, and kept the boundary of B explicit. We said that we're going to make a total transformation of the field. So there will be a bit that is internal, and then there will be a bit that is space-time transformation. So we look at the total variation of the action. We rewrote that as an integral over a bulk term. The bulk term became exactly the Euler-Lagrange equations that vanish because we're looking at classical equations, equations of classical solutions to the classical equations of motion, and a boundary term. Now we gave these boundary terms names. So this term, which we wrote down explicitly what it is, we called it the stress tensor, right? And then there is this extra term. When we have a symmetry, this must vanish. Not a general transformation, not a symmetry, but it happens to be a symmetry. If it is a symmetry of the action if this vanishes, right? So we parameterized our variation of space-time and variation of the field using these epsilon parameters. These are infinitesimal parameters because we said these are differentiable transformations, so we could look at them infinitesimally. And we just using this, we showed that vanishing of this term is equivalent to this equation, where J mu I are basically the conserved currents, that local currents that we define. And this is the conservation law, and we interpreted it why it's a conservation law and what are the charges that are conserved under the charges are basically integrals of the current inside B. It becomes a boundary term by Stokes theorem. Well, I forgot. I think I promised I'm going to review Stokes theorem. Okay, I'll try to do that in the next lecture. So we worked out 3 examples. Example 1 was translation. Then there was phase rotation. And then, the translation, space-time translations. We saw that the current associated, conserved current associated with this is the stress tensor. We took a complex scalar field and we did a phase rotation. We saw that there is a conserved current which associated with that. This is the conserved current. And then finally, we looked at space-time transformations. We saw that the conserved current associated with it could be written in terms of stress tensor. And it is conserved. The conservation equation is satisfied if and only if your stress tensor is traceless. And we interpreted this as the fact that for non-relativistic theories, you also have a stress tensor, energy momentum tensor, but it need not be traceless. Sorry, symmetric. I said traceless? I misspoke, sorry. Symmetric. Because, yeah. All right, very good. Any questions from the last lecture? All right. So today we're going to talk about another part of this story, which is this triangle that I was drawing at first when we were discussing local symmetries, which is the connection between symmetries and group representations, in particular, Wigner's theorem. So we're going to say, what is a group? Why is it relevant for physics? What's a group representation? And we were going to give examples of important differentiable groups, Lie algebras. These are things that appear in physics as continuous differentiable symmetries, and they play an important role in Noether's first theorem. Right? Is it clear what we're going to say today? So we're going to talk about the other side of this triangle, the connection between symmetries and group representations. And yeah. All right. So let's get started. If there are any questions at any point, please stop. All right. Symmetry transformations form a group. Let's just orient ourselves. This is, let's say, a Lorentz this is a Poincare transformation. This is a Lorentz bit. This is a translation. And a transformation could be labeled by the Lorentz matrix, transformation matrix, and a particular translation. We're going to call that G. So it's a symmetry, meaning that under the action of this G, S of X becomes S of X prime. So it's unchanged. Now, if S of X prime, if S of X prime and S of X are the same under some G1 transformation, then you could do a G2 transformation, which is another symmetry, sending X prime to X double prime. And of course, there will be a new symmetry transformation that connects X to X double prime, right? So this is a composition law for symmetry transformations. Symmetry transformations, when you compose them, you get another symmetry, right? Of course, their identity, doing nothing, is a symmetry transformation. And if something is a symmetry transformation, the inverse is also a symmetry transformation. So putting all of these properties together, we get a group, symmetry group. So what is a group? Mathematical group is a set of elements which has a multiplication operation. Multiplication operation is composing transformations, right? It should be already clear that general transformations need not commute, right? Performing transformation 1 and then 2 need not be equal to performing transformation 2 and then 1, right? The order might matter, but we're going to get it. So it has to be close under multiplication, meaning that if you have two transformations, after multiplication of it, composition of them should be another transformation, which is a symmetry. It should be associative. There will be an identity element in there, and there is an inverse, right? This is what's a group. This is what mathematicians call a group. So symmetry transformations do form a group. That's why we talk about groups in physics, right? Now, we said different in our discussion of Noether's theorem, we use differentiable transformations, right? And that was important because we wrote, I kept saying the words infinitesimal transformation, right? So differentiable transformations form some sort of differentiable group that needs to be clarified. But colloquially speaking, that's what the Lie group is. It's some sort of a group that could be, you could differentiate. You could talk about infinitesimal transformations. And then by very crudely speaking, that's the picture. All right, so is the idea of a symmetry group clear? All right. Good. So let's work out, I'm going to try to explain, build up towards the definition of a Lie groups, which I might not actually even define properly, by examples. So the first example is going to be an example of rotations on a circle. So I have a set S1 circle, right, which are parameterized by some parameter theta naught. And I'm going to look at the transformations, which are just like rotations, sending theta naught to theta. Now, of course, rotations form a group because you can compose rotations and get another rotation. And this theta parameter is the label that I could use to parameterize my group, right? So theta 1 is translation by angle theta 1, theta 2 is translation by, angle theta 2, and then I can compose them, right? I can compose them and get a translation by theta 1 and theta 2, right? So composition law is just addition of angles, mod 2 pi or whatever is your circle. Doing no rotation is your identity, and the inverse is just rotating in the opposite direction, right? This is an abelian or commutative group because composition, the composition rule doesn't understand order, right? Performing transformation 1 and 2 is the same as performing transformation 2 and 1. And moreover, your group transformation is the same thing as the space that it was acting on, right? So the group is also a circle, also S1. You can clearly see that I'm using the same parameterization for both, right? Therefore, because X was a smooth manifold and it has derivatives and all that, your group is also going to be smooth manifold. It will have it's the same manifold, right? So it's differentiable. So it makes sense to talk about differentiable transformation. Now, an infinitesimal transformation is the rotation vector. It's the tangent at any point by del theta. It's a tangent vector. And the generators of the group are these infinitesimal transformations, the vectors that generate infinitesimal transformations, this del theta here, right? So the terminology is like this. The group, well, okay, we're going to get that. Is this very, very simple example clear? We're going to build up on this and go forward. Now, let's consider the same group of rotations acting on R2, two-dimensional Minkowski space, right? So it's the same group, but this time I'm representing it using matrices because the action of it on R2 is a little bit more sophisticated. I repeat, it's the same group, but I'm representing it. The keyword here is representing it differently, right? How do I represent it? Using matrices, right? And multiplication, composition action of the group is matrix multiplication. That's important. That's why I do this, right? So my group is still S1, still parameterized by an angle theta, rotation by angle theta, and the angle theta is mod 2 pi, right? However, the set is acting on, the representation has dimension 2, right? It's 2 by 2 matrices acting on X. So the infinitesimal transformations are these, there are generators, right? Which is basically you take this matrix and expand it around identity, the identity element, right? So you get, this is the expansion around the identity element. Now, the Lie group here is this S1, these rotation group. It's the exponentiation of the Lie algebra. The Lie algebra are these infinitesimal rotations, which I can think of as matrices, as vectors, rotation vectors, right? This is the terminology. So there's a Lie algebra that you exponentiate to get a Lie group. And this is just basically moving along a tangent vector. That's what it is, right? So you generate the group by moving along the tangent vector. Think of the elements of Lie algebra as velocity vectors, and space-time as your group, right? So the Lie algebra is the tangent space to the group. Now, those examples are trivial. Let's move towards more fancier examples where you can see actually what's the point of representation. So let's pick the first non-abelian example. These are rotations of R3. So these are rotations in 3 dimensions, right? So from classical mechanics, you'll probably learn about Euler angles, right? So there's alpha, beta, and gamma. So you could parameterize your group using these 3 parameters, but the composition rule, you just don't know the a priori. It's complicated. How do you do it? How do you figure out the composition rule? What does it mean to compose these 2 guys? Well, you'll have to represent them as matrices, right? You should have a map from the group elements to matrices, then multiply matrices to get the result, and then map back to see what is this element of the group that corresponds to the composition, right? These matrices, these rotation matrices are called representations because abstractly the group, you don't really know how to, you have to represent it. Otherwise, it's a very abstract object, right? Representation is just like a way of writing it down as a bunch of matrices, and where multiplication is matrix multiplication. Of course, it's non-commutative because of the famous fact that rotations in 3 dimensions do not commute. The set of generators will form a Lie algebra, the tangent space of the tangent space. We're going to see that in a second. So I'm not going to write down this Euler angle, like this is something you can remember from classical mechanics, or you can look up the Euler transformations, right? So basically what you do is, in Euler's way of writing it, you first rotate around, you rotate around axis Z, then you rotate around the new axis Y, then you rotate around the new axis Z again. That's Euler's representation of it. But more generally, you can think about infinitesimal rotations, around the Z x-axis, which is by this matrix. This was just previous, it's just that this guy we already had, but it's in one higher dimension, and x is kept fixed. By just swapping x, y, z, these are infinitesimal rotations around y, and this is infinitesimal rotation around z. Right? Now you can see that these matrices satisfy an algebra. This is a commutator, right? Lx and Ly is Ld, blah blah blah. This is called a Lie algebra, right? So you have a Lie algebra, which is like the properties of the tangent vectors. You exponentiate that to get a Lie group. Any questions? Are these ideas clear? All right. So let's now, with that, formally formulate what a representation of a group is. We said abstractly what a group is. We first motivated in physics a symmetry transformation, then we define this abstractly. Now, what is a representation of a group? There's a quote-unquote linear here, but all our representations in physics, all the ones that we care about in this course, are going to be linear representations. So a linear representation is a map from the group elements to matrices, such that matrix multiplication is matrix multiplication. Group multiplication is matrix multiplication. It's a represent, for lack of a better term in English, I would use the word representation. It is a representation of my algebra, my group. Right? My group is this abstract thing where I don't know how to write down the multiplication rule. Multiplication rule, a good way of writing it down is in terms of these matrix multiplication, right? So a representation R is a map from the group to matrices. For example, I don't know, you could have two angles, theta and phi, and you're representing that with R and theta and phi, such that matrix multiplication, group multiplication is simple matrix multiplication. Now, the identity element of the group is going to be the identity matrix. Let's just assume that for now. The inverse of the representation of the inverse element is the inverse matrix, right? And of course, in general, it's non-commutative. All right, that's what the representation is. The distinction between group and representation is something that mathematicians care about. In physics, we care about this because of, well, yeah, I said what I said. All right. Is the idea of representation clear? So I'm going to go through the most important example, some of the most important examples that will come up in your in physics, right? That's the rest of this lecture, pretty much. We'll see how far we get. So rotations, right? ON. Consider as example number 4, rotations in n dimensions. So what I'm building on is just generalizing rotations, right? The group is called ON. One way of defining them is in terms of a representation. It's the group of orthogonal n by n matrices. Orthogonal means R transpose multiplied by R is identity. Right? So you could view this group as some sort of an internal transformation, internal symmetry. Right? How? Let's say you have n copies of the field. This could be, and this is some sort of internal transformation that at every point rotates the fields among themselves. So it's a rotation in the field space, right? This was an example of this was in the case of complex scalar we saw, and SO2, right? Special orthogonal transformation. We're going to say that in a second. So what does it asymmetry of? It preserves the inner product, which is phi transpose dot phi for these vectors, right? That's just yeah. This is the notation for repeated indices are summed over. How do you see that it preserves it? Well, take phi, act with matrix R on it. Takes phi, act with matrix R on it. The inner product is the transpose of here, inner product transpose here. Well, you could just write it as this matrix multiplication. Because we define R transpose R to be our identity, this is invariant. So it leaves the inner product invariant, which means that if you construct your action using terms like this, for example, if you write down any potential that looks like this, and your kinetic term that is like this action I wrote down has this symmetry. So here I'm taking the point of view, that we discussed this in the last lecture. You could say that I have some sort of physical system. It has a bunch of symmetries, right? I see, for example, there are a bunch of variables, and the rotation among these variables is an internal symmetry. So now I want to write down a Lagrangian for this, a Lagrangian density, some action principle. Because it's a symmetry, I have to implement that symmetry. So I'm confined to terms that look like this. The kinetic term, if it is to respect the symmetry, is going to be like this, and the potential term is going to be like this. It has to be a function of the inner product, because the inner product is preserved, is invariant. Now, of course, this formula tells you that the determinant of R transpose times determinant of R is identity, from which you learn that determinant of R is either +1 or -1. Now, if you restrict to set of orthogonal matrices, n by n matrices that have determinant 1, under multiplication, the determinant doesn't change. That forms a subgroup of ON. It's called SON. So these are a group of n by n orthogonal matrices that have determinant 1. That's SON. So SO2 is the rotation matrix we wrote down. Is the rotation thing we wrote down. And SO3 was rotations of the sphere. All right, any questions about ON and SON? I assure you this is not the last time you deal with these. As long as you're in physics, you're going to be dealing with one of these groups. Questions? All right. Now let's give a bunch of other examples. I'm going to go through 3 other important groups. UN, SUN, OD, 1, or SOD, 1. These are Lorentz groups. Okay. So what is UN or SUN? So I'm going to describe it in terms of a representation. Take your n-dimensional vector, but now take it to be complex. It's a complex vector field. So it's n-dimensional complex vector field. Now, I'm going to look at the group of unitary matrices. A unitary matrix is a complex matrix such that U dagger U is U dagger equal to identity. This is the complex version of orthogonal matrices, right? Where transpose is replaced by dagger, right? Complex conjugation. Now, what does this leave invariant? What is this a symmetry of? It's the symmetry of the inner product of this form. Phi dagger dot phi, right? How do I see that? Well, I rotate each of these guys. by U, and then because this is inner product, I get phi dagger U, and that is equal to identity. Now, because U dagger U is one, the determinant is a phase, right? You can restrict to the set of UN matrices, right? Unitary n by n matrices that have determinant one. That's a subgroup that's called SUN. So you might have heard the statement that the symmetry group of standard model of particle physics is U1 times SU2 times SU3. I think now you should know what it is all about, what the group is. All right. So here I'm representing it again as an internal symmetry, right? I don't have to, but I'm representing it as an internal symmetry. Now, the next example is we're going to discuss are OD comma 1 or SOD comma 1. So let me just make a comment here. So when we talked about OD, what this was keeping preserved. So this inner product here, you can think of it as a case where the metric, so there is a metric, but the metric is 1, 1, 1, like this, identity, right? If you just do the same exercise, but flip the sign of these guys, go to pick a metric, which is like Lorentzian, then your group, the same group is going to be OD comma 1. So how is it? You define your inner product this way, right? Using a Lorentzian metric. And this is your inner product. These are real vectors, say. So a matrix transformation, a transformation I'm going to represent it using these matrices lambda, right? So these are Lorentz transformation matrices. And the very fact that it has to keep this inner product invariant, this inner product had a name in relativity, right? It was proper length, right? This is a proper length. So it has to keep proper length invariant, right? So that just going through the same exercise, you see that it should act in the following way: that Lorentz transformation matrix transpose times flat space metric times lambda should be eta. This comma 1 is there to just remind us that the metric is basically diagonal and just proportional. It looks like identity, except that the sign of one of them is different. It's not too much of a stretch of imagination to imagine this group, right? That's where you're preserving a metric which has m plus signs and n minus signs. Now, if the determinant of lambda is 1, we call that SOD comma 1. That's going to be important. Distinction between the two is going to be important in quantum field theory. That is where these CPT, charge conjugation, time reversal, and parity are going to come about. The distinction between these two are precisely where this, so yeah. But I want you guys to first really get comfortable with these groups. I could have this Lorentzian metric as some sort of imaginary internal space, field space, right? No problem. I can just design it like that. We have models like that in physics. All right, any questions?
Do we care about the orthogonal sub of the Lorentz group?
We will get there. You're saying that the cases where the matrices that are in OD comma 1, but they're not in SOD comma 1. Yeah, we'll get there. The distinction between the two will become important.
Okay.
Any other questions? All right. Now I want to remind you of something from basic quantum mechanics, and we're going to go through this in more detail in the next lecture. but it's something that you'll learn, but perhaps it wasn't explained to you in this language. But it's a very familiar concept, hopefully. A group can have many inequivalent representations. So we said a group representation is a map from the elements of the group to matrices, right? And these matrices act on a vector space, right? Matrices act on a vector space. So it's a vector space V to V, right? That's what a matrix is. So when I talk about inequivalent representation, we're not talking about the dimension of the representation. We're talking about the dimension of this vector space V. You could have representation of the same group in different dimensional vector spaces. A very familiar example is SU2. So SU2, I'm gonna remind you of various representations of SU2 you know about in different dimensions. So spin half representation is when you realize SU2 as special unitary 2x2 matrices. So it acts on a two-dimensional complex vector space, right? This was precisely the description I use here. Right? Here, the vector space V is a two-dimensional complex vector space. Where was it? Okay, here. So these like alpha, beta vectors. And here the generator, so this is a Lie group. In this representations, there's a tangent space, right? There's a Lie algebra. What are the generators of the algebra? You know them pretty well. These are the Pauli matrices, sigma x, sigma y, sigma z. But you also know about spin S representations for all sorts of different S. Spin 0, spin half, spin 1, spin 3 halves. The dimension of these representations are 2s plus 1. And the generators are j plus, j minus, jz, right? So jz, so we label the representations. S is the spin, and m is this parameter that runs from minus s over 2 to s over 2. Sorry, minus s S. Sorry about that. So it's 2 plus m plus 1 dimensions. Now j plus and j minus 1, j plus and j minus are raising and lowering operators. If you're not very comfortable with this, I remind you YLMs of quantum mechanics are precisely different dimensional representations of the group SO3. So when you solved hydrogen atom, those YLMs, spherical harmonics you found, these were various dimensional representations of the same group, SO3, rotations of sphere. All right, is this idea clear? So now, with that in mind, you should put this next to all the things that you have learned so far. When you write down an action, when somebody, as a physicist, comes to you and says, hey, I have a vector field that transforms as, say, in a particular representation of symmetry group SU2, right? That you already know how to write down the action for that theory that's free, right? So you hear this a lot. I have a field theory that has symmetry group, I don't know, SUN, and my fields transform in a particular representation. Right? To describe the theory, I have to tell you what the representation is. That will tell you how to write down the action. Is this idea clear?
Could you repeat it once more?
So if I come to you and say, I have a set of scalar fields that transform, and I have a symmetry group SU2 that acts on it, I haven't described to you the theory yet. I have to tell you in which representation, right? SU2 could act on a complex vector field, right? I can act on a complex scalar, right? Two-dimensional. Sorry, SU2, two-dimensional, two complex scalars, right? Or it could act in higher dimensional representations, right? So I have to tell you, it could act, it could have all sorts of, I will just give an example. It could be transforming some other spin, right? That's why in physics, we often hear, so for example, when you talk about SUN super Yang Mills, that's the theory that, I don't know, you might you might know nothing about. But what you need to know is that there are gauge fields in there that transform in the adjoint representation. So I haven't told you what the adjoint representation is, but it's a particular representation, right? So that is what you hear in the description of the theory. When somebody gives you the description of the theory, in a lot of cases, that is, they're telling you how to write down the Lagrangian. Because the principle is that you take the symmetry group and the representation, you write down the most general action possible that is smooth, respects the symmetry and symmetries, and it has the lowest number of derivatives. Can anyone say why the lowest number of derivatives? Go back to lecture 1. Where do field theories come from? They come from low energies, right? So you just take an action and write down, do a derivative expansion, right? Derivative expansion and power expansion of the field. And knowing the symmetries, that is actually a description of the theory. So what I'm telling you about is this old idea of Landau for how to build effective field theories that have played a major role of 20th century physics. It won a Nobel Prize. It's just revolutionized condensed matter and field theory. Anyway, all right, any questions so far? So far, I just gave a bunch of examples of symmetries. I said what a symmetry group is, what is a representation, and why is it important. Now, the next step is Wigner's theorem. So up to here, everything I said was just math and classical physics. I'm going to use the same mathematics to tell you something about quantum mechanics. The exact same mathematics is telling you something about quantum mechanics, and that's called Wigner's theorem. Why is that? You're going to see that in a second. So the question was, what is a quantum symmetry? Well, it's easy based on what we said. We said that symmetry should be represented somewhere on some vector space. It should be some matrices in some vector space. Well, in quantum mechanics, we have a canonical notion of vector space. It's the Hilbert space. And the symmetry was supposed to preserve the inner product of that vector space. Well, there's an inner product in the Hilbert space. So a symmetry better preserve that. Now, there's a physics interpretation associated with that. So a quantum symmetry would be some map from your group, right, to a set of operators in the Hilbert space. These are matrices in the Hilbert space. It's a symmetry if it preserves the Hilbert space inner product. Why should it do that? Because the Hilbert space inner product is physical. It's the overlaps, right? It's the things that I can observe, well, hopefully. I'm lying a little bit. And I'm gonna explain that lie in a second. But overlaps are these like scattering or like, overlaps are the physical content of my theory, right? So if it's a genuine, honest to goodness symmetry, better preserve that. So here are vectors in the Hilbert space. This is a representation of my symmetry, right? UG and UG here. It better preserve this guy. Well, you already know what the answer, what this says. It says that they better be a unitary matrices. Because it's supposed to preserve the inner, I mean, all that Hilbert space is just a complex vector space, right? With an inner product. So Wigner's theorem tells you, and you also want linearity, but we're only talking about linear transformation, linear representations here. So you get unitary matrices. Wigner's theorem tells you that symmetry in quantum mechanics better be represented as a unitary matrix on the Hilbert space. That's what the message is, right? So it tells you how to go between symmetries and representations. Now, I lied a little bit. The overlaps are not the things that are observables. probabilities are observables, which are the overlaps squared. So in principle, my symmetry can be, it can, instead of leaving the overlap invariant, it could be equal to the overlap complex conjugate. And there's no way for me to tell them apart, in principle. If I'm only measuring probabilities are the only things that come out of my measurements, a symmetry can do that. This is why, if you read Wigner's theorem, it tells you that symmetries are represented using either unitary matrices or anti-unitary matrices. So anti-unitary matrices correspond to anti-linear transformation. So these are a little bit counterintuitive. Is there anti-linear mean that if you multiply these guys, when UG acts, as it goes through these complex numbers, what comes out of it on the other side will be the complex conjugate of it. The notion of a dagger for anti-linear operators is a little bit tricky, but once you work it out, you're going to get this. Now, in principle, most of what we discuss in physics, most of these symmetries we're discussing are going to be represented using unitary representations. There are special examples where you're dealing with anti-unitaries and they come up in quantum field theory. Hence, that's why I say this. There are important examples of symmetries in nature. One important one is CPT. It's a very famous example. CPT is represented on the Hilbert space as an anti-unitary, not as a unitary. And I hopefully explained to you guys what's the difference between the two. The difference is between there's room in there because you don't measure overlaps, you measure the normal one. Any questions?
I'm a bit confused about anti-unitary matrices and the definition.
Yes.
So the C1 phi1 plus C2 psi2, that's our standard Ket vectors, right?
Sorry, where are you talking?
This
here?
Yeah, here. The
No,
C1 psi1 plus
not
C2
at all
psi2.
standard. What is standard is the linearity is standard.
Okay.
Right? A linear operator, if you take your psi and multiply by a phase, a linear operator, so here, take some wave function quantum mechanics, apply a phase, and then act with, I don't know, some sort of a unitary transformation, say time translation, right? E to the power of IHT. Is simply the statement that I can commute a phase with an operator with my symmetry transformation. I can do that. Right?
Okay.
Now, for these symmetries, but some symmetries need not be like that. Based on the example I gave you, you know immediately an example which is not represented as a unitary. Do you have any ideas? The example here I worked out here was intentional. Well, think about it. You do know of symmetry transformations that are not unitary. So is it good? So this anti-linearity is something weird.
Okay.
I assure you, only talk about linear or anti-linear. There's nothing else. We never talk about anything else. All right. Any questions?
Is the anti-unitary operator you refer to the complex conjugation operator?
Complex conjugation operator? Yeah, time reversal. CPT is one example, or time reversal. The anti-unitary, one such example is time reversal.
Okay.
All right. Okay. Any questions? So let me just summarize what I've said so far. We started by talking about symmetries. We said they form a group. Symmetries these are not arbitrary random things. These are things that symmetries are a system, right? One manifestation of that was Noether's theorem, right? These are transformations that preserve the action. Now, they form a group. We talked about the fact that groups are way too abstract. We want to know how they act. If they want to know how they act, what this content of the transformation is, you need a representation. That representation, the same group can have many inequivalent representations, right? And that is part of the description of your physical theory, right? And we went through a bunch of important examples. These are because we're primarily concerned with Noether's current, Noether's theorem, first theorem, right? We're concerned with differentiable transformations, that are symmetries. And that's why the context of Lie algebras or Lie groups come about, right? So Lie groups are these differentiable manifolds of groups that are differential. They're these manifolds that are groups and they're differentiable. And the tangent space of them is basically describing to the Lie algebra, right? And we gave a whole bunch of examples. If this idea is too abstract, I gave a whole bunch of examples, right? So rotations are these examples. Lorentz transformations are these examples. Translations are these examples. I didn't mention that, but it's not hard. It's not much of a stretch for you guys to go from what I've said to this, right? So these translations are non-compact versions of this, right? For example, the group could be R or RD comma 1. Those are space-time translations, right? All right. Then we talked about UN, SUN, how the determinant was an important part of the story, right? I think those are all the groups that I mentioned. Then we went through Wigner's theorem that basically said, okay, based on the things that we already know about symmetries and how they act, we could pick the representation, the vector space on which the symmetry acts as the Hilbert space. Now, the very interpretation of a symmetry, quantum symmetry, is that it should keep the overlap invariant. That will tell you that this is the content of Wigner's theorem. That's either unitary or anti-unitary. Good. Every time you have a group, it could have unitary it might have unitary representations or might not have unitary representation, right? So a unitary representation is further constrained. You don't want you insist on representing your matrices only using unitary. Good. So, for example, there are examples of theories where they do not have any. You can probably read in between the lines if you know a little bit of group theory. There are very important examples of Lie groups that do not have any finite dimensional unitary representations. So if you want to insist on unitary representations, you always have to land in infinite dimensional spaces. But if you relax unitarity, you can talk about finite dimensional representations. All right, any questions? So based on what I've said, you already realize that, oh, in the Hilbert space, I made a little bit of a leap. My physical states are not vectors in the Hilbert space. My physical states are rays. If I take a vector, multiply by number, right? Or multiply by phase. If I take all vectors in Hilbert space and apply all of the vectors by phase, I'm not talking about relative phase. I'm talking about multiplying all the vectors by phase. Or if I take a vector and just multiply by a number, right? Nothing in physics should change. Physical states are rays in the vector space, in the Hilbert space. That tells me that, oh, actually, when I'm constructing representations, so I had the rule that multiplication of the matrices had to be the group multiplication, right? So I was setting this guy to 1. But if there is this global phase that I can never observe, I should relax that condition. It's possible that, it's imaginable, it's conceivable that there are some representations. So there are some way of representing the matrices on the Hilbert space, that when you multiply these guys, you don't quite get, you have G1, G2, you get that up to a phase, but because it's a global phase and it applies the same way to all vectors in the Hilbert space, I can never distinguish the two. This is the notion of a projective representation, right? I'm modifying the definition of a representation where matrix multiplication had to be composition, group multiplication. Now I'm just broadening up, right? Of course, any representation is projective as well, but there are projective representations that need not be representations. If this guy, this phase, is non-trivial. But it's something that you could motivate mathematically, but physically the motivation is pretty clear. Are we good? This issue really comes up in the Hilbert space, right? When we're talking about representation theories and symmetries, we said that I can discuss this at the level of classical physics. In classical physics, I have less motivation to consider projective representations. Right? In quantum mechanics, this is sort of imposed on me by the virtue of the fact that these global phases I can never observe. We will see that there are important cases of projective representations, and then, well, they play a big role in physics. Is the motivation clear? Are there any questions?
So Wigner's theorem says that any representation must be either unitary or anti-unitary.
Yes.
No, can we extend it?
Any symmetry should be represented.
Any symmetry should be represented by such a unitary anti-unitary transformation.
In the Hilbert space.
In the Hilbert space, yes.
Yes.
What about projective representations?
So these are still unitary and anti-unitary.
Okay, yeah, that's okay. I understand. Gotcha.
Yeah. So Wigner's theorem is the side of the story that says what should U and UG be. Right? So that was just talking about preserving the inner product, right? This was not about multiplication. There's this further constraint of freedom in multiplication.
Okay.
All right. Any other questions? All right, we're doing pretty well, so we're going to get started with Lie algebras. All right, actually, it's a good moment to pause and ask for questions, because in the remainder of this lecture, what I'm going to do is that I'm going to take the idea of a Lie algebra and a Lie group and run with it. Just formalize this abstractly, and there's a reason to do that, because lots of theories that we're interested in, QCD, and quantum chromodynamics, all these theories, you will have to get used to the language of Lie algebras and Lie groups, and this language actually has deep physical consequences. All right, are there questions?
So I just want to clarify just basically what I just asked you about. So Wigner's theorem just says that what kinds of representations we should care about.
In the Hilbert space.
In the Hilbert space.
Yes.
Okay, thank you.
Yeah. Yeah, Wigner's theorem is, correct. Okay, so now let's talk about Lie algebras. And for clarity, to avoid confusing you guys, I'm going to first focus on the case that I'm talking about non-projective representation. So I'm just talking about representations, right? Because that's an extra layer of complexity that we'll leave until the next lecture. So for a second, forget about the comment I made about projective representation, non-projective representation. Sorry. Yeah, projective representation. I'm going to view these guys as transformations, symmetry transformations of my classical theory, right? Therefore, it's natural to represent them using representations. All right, so let's go back to the original picture we had, right? What was the Lie group? Lie group was this smooth manifold, very nice manifold. These are spheres and like really nice manifolds. And there was a tangent vector. There's an identity. There's a point you could pick as identity, right? And then there's a tangent vector. There's a tangent space. Sorry, there's a tangent space. And tangent space is spanned by a bunch of orthogonal vectors. And those generators, we recall that every point in here in a representation is a matrix. So the tangent space, we're talking about tangent space in matrices. So that means that you have to take your matrices and expand them. That's what we did for the case of SU2, right? Rotations, SO2. We wrote down this cosine theta, minus sine. We expanded that and we got this Lie algebra, these sigma x, sigma y, sigma z's, right? So here we're always dealing with matrices representations. Now let's say near identity, I'm gonna parameterize my my element in this tangent space using a bunch of parameters, theta 1 to theta k. Sorry, theta k, theta 1 to some theta, that clearly is the dimensionality of G, right? The dimensionality of the tangent space is the same thing as the dimensionality of the group, right? So I'm just like using this vector notation, but it doesn't really mean much. It's just a bunch of, yeah. So when I multiply two of these guys, right? I should, for now, now I'm talking about a general Lie group, right? For a general Lie group, for particular Lie groups and particular representations, I knew exactly what these are, right? So for example, for rotation matrix, there was a map from theta to u theta, right? And I was multiplying these guys, and that I was getting some answer here. I was inverting the map to read off what this f of theta and theta prime is. But abstractly speaking, this is u of theta prime. They multiply to give you u of some function of theta and theta. So we're gonna explain a little bit more, explore the properties of that function. So let's take two particular elements, theta k and theta prime k. And this is gonna give you, whoops, that is not a good notation. Let's say K and L. No, that's not what I want to do. Yeah, K and K, sorry. Okay. So first thing you notice is that because u of theta k and u of 0 is going to be u of theta k. Why? Because u of 0 is just the identity element, right? You can expand f of k theta prime in terms in the following way. There will be theta k and theta k prime, right? And second order terms. Is this logic clear? This says that if you, whatever is my expression, if I set theta prime to 0, I should get theta k, right? Hence this term. But I can switch the rule of theta and theta prime, and then it tells me I get this term. That fixes for you the linear term. For the second order term, you write down the most generic thing possible. Again, repeated indices are something. All right. So what am I doing? I'm taking this matrix and I'm expanding it as identity matrix plus I theta k lambda k. I put a hat to remind you guys, these are matrices, right? And then there will be second order matrices. Now, it's pretty clear from this term that this second order matrix is going to be symmetric. It's a good exercise. Maybe I'll ask you guys to do it in your homework, but it's somewhat trivial. Is that if you take the composition law, this law, and expand it to a second order, you find the following relation between the second order term and the first order term. So this symmetric second order matrix should take the following form in terms of the first order matrix. It's just an exercise. You expand this to second order, you put the left hand side and right side equal, you get this. So the important point here is that these coefficients you should keep track of. We're going to say that in a second. All right. Now, importantly, you notice that this is symmetric. So if you take the left-hand side, the right-hand side, and you anti-symmetrize it, it should vanish. That will tell you that the commutator of these lambda k, these matrices, these elements of the Lie algebra, are basically a bunch of coefficients. They're called structure constants of the group. which are the anti-symmetrized versions of this FMKLs. All I'm doing is that I'm just like imposing, I start with a general ansatz of what it should be. I'm just imposing the constraints of multiplication being represented. The representation constraint that element multiplication should be represented by matrix multiplication, and the fact that these are smooth, I can just expand them arbitrarily, right? They're differentiable. It's not just smooth, they're smooth, they're differentiable, right? So now you already see a connection, a Lie algebra emerging. Lie algebra was this thing, was some sort of commutation relation in between these tangent vectors, right? Each of these lambda k's are tangent vectors in this tangent space, right? They're element of my Lie algebra, and they have to satisfy an algebra with a bunch of coefficients, and these coefficients show up in the expansion of U. Or F, sorry, F. This is a connection between Lie group and Lie algebra that we're building on. Now, if the group is a billion, all of these guys vanish. And you can show that UG1, UG2 is UG2, G1. An example would be translations, RD, 1 or U1. But in general, it's not. Therefore, these guys are not zero. They're structure constants in the group. They're very important. Now, you still have another condition to satisfy. If you multiply F theta and, sorry, U theta and U theta prime, followed by U minus theta prime, U minus theta, you should get identity. It's a little bit more counterintuitive to know why this constraint and nothing else, but if you play around with this, you'll learn that this was an extra bit of constraint that we had to impose. From this, with a little bit of just algebra math, it follows that your lambda k's and these FMKLs should satisfy this equation, from which you read off the fact that the FMLKs should be symmetric. Right? So let's recap. We learned that basically this FKLMs are the important information in your Lie algebra, in your, sorry, Lie group. They decide for you the commutation relation of the Lie algebra, and these guys are symmetric. Right? So far, that's all we've learned. This tells you, if you just plug this back into this tells you that the second order matrix is actually fixed in terms of the first order. By repeating this, you could just argue that U of theta is basically an exponentiated version of the Lie algebra generators. That's just a statement, the intuitive statement that if these vectors move you along a path, as you move along this path, you're moving along your manifold. So if your Lie group is such that we're using with these paths, we can get everywhere, right? Then the Lie algebra knows it all. Now, here's an important thing that comes up. Consider a group that is O2, or O3, sorry. For example, O3. These are rotations of a sphere, right? This is a sphere. But we said there are elements of this guy that have determinant 1, and there are elements of this guy that have determinant -1. The elements of the guy that have determinant 1 are mere identity. So this whole story that I said holds for them. So if you take the identity element and start moving along the tangent vectors, you're only going to explore the SO3 part of the manifold. You're never gonna go from determinant 1 to determinant -1, right? So this is related to being simply connected, blah, blah, blah. But there's topology in here, right? But these connectedness, simple connectedness, these things have dramatic physical consequences. All right. Now I want to finally show you guys a table of important groups that come up in physics. I haven't defined this guy for you guys yet, but UN is the group, is dimensionality of the, so these are representations I'm talking about, right? So I can represent them using Hermitian matrices, right? And the dimensionality of the group is n squared. SUN is n squared -1 because we said that the determinant is a phase, and by setting it to 1, I kill 1 degree of freedom. In the Lie algebra language, that is setting the Hermitian operators to picking them to be traceless. So an example here would be U2, right? At the level of the Lie algebra, U2 is generated, so it's 4-dimensional, right? What are the generators of the Lie algebra? Identity, sigma x, sigma y, sigma z, requiring that its SUN will kill this guy and restrict to Hermitian, traceless Hermitians, and these are the good old polymorphs, right? So that's the distinction between U2 and SU2. SU2 is generated using sigma x, sigma y, sigma z, but if you want to generate U2, you need the identity guy as well. Hopefully this is familiar from physics. If this is not familiar from physics, we've got some problems. But these generalize, right? So ON is n times n minus 1 over 2. These are anti-symmetric matrices. So symmetric matrix, hopefully you remember what a symmetric matrix is. It's just the transpose is equal to itself. Now SON is the case that you put the traceless case. This is the setup where you say, I'm going to set the determinant to be 1. The dimensionality of the group doesn't change. Can anyone say why? What is the extra condition that takes me from O1 to SON? The determinant of R has to be 1. What are the choices for the determinants of ON matrices? Anyone?
1 and -1.
Exactly. So here you're not really changing the dimensionality of your manifold. You just had 2 copies of it, right? You're not killing any parameter. You just, by fixing it to be 1. This is to be compared with SUN, where determinant of these guys was a phase, right? And here, you fix it to be 1, so you kill a degree of a continuous variable that brings the dimensionality down by 1. But here, you're just saying that, oh, I had 2 different copies of it. I'm just going to pick 1. All right, and SPN is another symmetry group that comes up in physics. We're not going to talk about this for now, but I just want you guys to put it next to this. This is pretty much, for the most part, unless you do some advanced stuff, these are pretty much most of the Lie algebras, the important Lie algebras and Lie groups we work with in physics. They're all over the place. They're absolutely all over the place. Just using these groups and their representations and free fields, we have modeled so much out there in our nature. It's incredible how far we go. Well, for one thing, we've modeled standard model, which includes everything but gravity. All right, any questions?
So the difference between ON and SON is like ON has like 2 disconnected copies of SON, and we just like select one of them, so to say.
Yeah.
Okay.
So let me do a summary of what I said, and I will say what I haven't said as well, right? So today, what did we do? We discussed the connection between symmetries and group representations. One important aspect of that was when the group was the notion of a quantum symmetry, where Wigner's theorem tells you that a quantum symmetry will have to be represented as a unitary or unitary or anti-unitary in the Hilbert space. We said because in Noether theorem, we're concerned with differentiable transformations, and recall what a differentiable transformation is. It's just an intuitive thing that you can talk about infinitesimal transformation, right? We are dealing with groups that are differentiable, and these are naturally the one simple context where this appears are Lie algebras and Lie groups. So Lie algebra is a tangent space, and the Lie group is the exponentiating function. There might be disconnected pieces, blah, 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 of course. And we went through a whole bunch of examples. And yeah, I think that's pretty much what I said. All I said. When we discussed what a general Lie algebra is, and we saw these FKLMs, these parameters are important, and they help us, eventually they will help us classify Lie algebras and Lie groups. And here's a table that's important. But why I haven't said is this. If you have a symmetry transformation that's not continuous, right? It still will have to be represented. So even for discrete symmetries, you have the story of representation theory. Even for discrete symmetries, you have Wigner's theorem. But the discrete symmetries are not going to be related to this story of Noether's theorem. Noether's first theorem doesn't have anything to tell you about discrete symmetries. Differentiability was important. Now, from the example of SON versus ON, you learn that you could construct these Lie algebra ON using transformations that are well, anyway, there are anyway, let me not, we'll get there. We'll get there in representation of Poincare. All right, any last questions?
One thing, like like we considered this property, which at least it almost seemed to come out of nowhere, which proved that the FMKL, those constants should be antisymmetric in K and L.
No, it didn't come out of nowhere. It was the antisymmetry. This one. No, wait, sorry.
No, down next page.
This one.
Yeah. I came out of this relation, right? This
yes.
U theta.
Yes.
So when I say I came out of nowhere, I meant
it was unclear why this was a new thing.
Yeah. So my question is, how do we not know that there are no more other relations like this, which can constrain them even more?
Answering that requires a little bit of Lie algebra theory and Lie group theory and taking a course on this. They are fully understood and classified. Of course, what you're asking is a little bit more nuanced. You have to just look at theorems and proofs, and you can. That turns out that these guys are so nice. You could pretty much classify a lot. You could do a lot of classification. Yeah. Okay. So I don't have time here to unfortunately teach representation theory, but just take it as a fact that this is it. All right. Any other questions? One little comment. So problem set number 2 is posted. Yeah, actually, no, I don't have any other comments. I do want to say one thing, which is this is an advanced graduate level, PhD level course. And I understand that the course is being taught on Zoom, but it doesn't make it optional for people to come. It's an advanced course. I'm not going to keep track of presence. That's cheap. That's not for me. But I just want to remind people that if you just don't show up to class on Zoom, which is like half of the class is not here, I think it reflects poorly on you and potentially on the grade that you eventually get. But I'm not going to keep track of presence. Anyway, thank you so much, guys. Have a nice day.
Thank you.